Multiple substitutions in a single integral. Okay, so let's move on to a new technique in integration. As you know, in the sections we've covered so far, we've focused on using a single substitution to tackle integrals. We learned how to cleverly change variables to transform a complicated integral into a simpler, standard form that we can easily solve. However, not all integrals are created equal. Sometimes, a single substitution just isn't enough. In more complex problems, a single change of variable might simplify things a little, but it won't get us all the way to a solvable integral. That's where the idea of multiple substitutions comes in. When a single substitution falls short, we don't give up. Instead, we use what I like to call a layered approach. Think of it like peeling an onion, or, as we'll see on the next slide, opening nested boxes. We apply substitutions one after another, sequentially, building on the simplification we achieved with each step. This allows us to progressively unravel the complexity of the integral until we can finally solve it. So, get ready to learn how to combine the power of substitution to conquer even the most challenging integrals. Understanding the concept. Think of a complex integral, the one we're trying to solve, as a nested box. Imagine you have a prize inside, which represents the final answer we're looking for. But the prize isn't directly accessible. It's inside a smaller box, which is itself inside a larger box. To get to the prize, you first have to open the outer box to reveal the second box, and then open the second box to finally reach the content, the prize. In mathematical terms, this nested box situation happens when the integral, what's inside the integral symbol, contains a function within a function. This is what we call a composite function. For example, a trigonometric function acting on an algebraic function. The key thing to remember is that after we perform our first substitution, the resulting integral is often still a composite function. It's like opening the outer box. We've made progress, but there's still another layer to peel back. We need to simplify it further. Now let's look at the general workflow, the steps we'll follow when tackling these multi-layered integrals. First, we perform our first substitution. The strategy here is to target the innermost part of the function, the argument of the inner function, or any particularly complex part of the integrand. The goal is to simplify the overall structure. Next, we have simplification. After making the substitution, we rewrite the entire integral in terms of the new variable we introduced. This should make the integral a little easier to handle. Then comes the second substitution. We look at the simplified integral and identify a new pattern that we can exploit. We apply another substitution, aiming to transform the integral into a standard form, something we know how to integrate, like a simple power of x or a basic trigonometric integral. Finally, we have back-substitution. Once we've integrated and have an answer in terms of our new variables, we need to express the answer in terms of the original variable, which is x. We do this by reversing the order of our substitutions, one step at a time. Okay, so let's move on to slide 2. This slide helps us understand why we sometimes need multiple substitutions. As we discussed on the previous slide, a single substitution often simplifies an integral. But what happens when that first substitution doesn't quite get us all the way to a solvable integral? That's where multiple substitutions come in. So, remember this layered approach. We'll see it in action on the next few slides with a detailed example where we'll walk through each of these steps. Detailed example. Okay, so let's move on to a detailed example, as you can see on this slide. We're going to evaluate the integral, which is represented by the capital letter I, and it's defined as the integral from 0 to infinity of tangent to the power of 4 of the square root of x, times secant squared of the square root of x, all divided by the square root of x, with respect to x. Now, if you look at this integral, it might seem a little intimidating at first glance. That's because it combines a square root function with some trigonometric functions raised to powers. Remember from the previous slides, when we encounter such complexity, we often need to use multiple substitutions. And that's exactly what we're going to do here. We'll use 2 substitutions to tackle this integral. Let's begin with the first substitution. As a general rule, it's often a good strategy to start by simplifying the innermost part of the integral. In this case, the square root of x is acting as the argument, the input, for both the tangent and secant functions. So, we'll focus on simplifying that first. Therefore, let's define a new variable, t, and set it equal to the square root of x, so t equals the square root of x. Now, this is a crucial step. We need to find how dx, which represents the change in x, relates to dt, the change in t. To do this, we take the derivative of t with respect to x. That is dt over dx. The derivative of the square root of x, which is x to the power of 1/2, is 1/2 times x to the power of negative 1/2. Or, in simpler terms, 1 over 2 times the square root of x, so we have dt over dx equals 1 over 2 times the square root of x. Now, to find dx in terms of dt, we simply rearrange this equation. Multiplying both sides by 2 times the square root of x, we get dx equals 2 times the square root of x times dt. This is a very important result because it allows us to replace dx in our original integral with an expression involving dt. This is the essence of substitution, and we'll use this relationship in the next step to transform the integral into a simpler form. Transforming the integral. Okay, let's move on to slide 4. As you recall from the previous slides, we were tackling the integral. I equals integral of tan to the power of 4 of square root of x times sec squared of square root of x divided by square root of x with respect to dx. And we've just completed our first substitution, setting square root of x equal to t, and finding that dx is equivalent to 2 times square root of x dt. Now, this step is all about applying those substitutions to the original integral. So, wherever we see square root of x in the original integral, we replace it with t. And wherever we see dx, we replace it with 2 times square root of x dt. This gives us a new integral. I equals integral of tan to the power of 4 of t times sec squared of t divided by square root of x multiplied by 2 times square root of x dt. Notice what happens next. This is a crucial simplification step. We have square root of x in both the numerator and the denominator. These terms beautifully cancel each other out. That leaves us with I equals integral of 2 times tan to the power of 4 of t times sec squared of t dt. Finally, we can pull the constant 2 outside the integral sign, giving us I equals 2 times integral of tan to the power of 4 of t times sec squared of t dt. Excellent, we've successfully completed the first substitution and simplified the integral. Now, if you look ahead to slide 5, you'll see that this new integral is now ripe for our second substitution. We're getting closer to a solvable form, and this is the power of using multiple substitutions in a single integral. The second substitution, resolving trigonometric powers. Okay, so let's move on to our second substitution. Looking at the integral we obtained on the previous slide, which was 2 times the integral of tangent to the power of 4 of t times secant squared of t with respect to dt, notice something special. We now have a situation where we have a function, specifically tangent of t, and we also have the derivative of that function, which is secant squared of t. Remember from your calculus rules, whenever you see a composition like this, a function and its derivative multiplied together, it's a strong signal that a substitution can greatly simplify things. So let's make our second substitution. We'll let tangent of t equal u. Now this is crucial. We don't just substitute the function itself. We also need to find how the differential, dt, changes. If tangent of t is equal to u, then the derivative of tangent of t dollar with respect to t dollar, which is secant squared of t dollar, is equal to do slash dt dollar. Therefore, we can write do dollar equals secant squared of t dollar times dt dollar. This relationship between do and dt is essential for changing our variable of integration, and we'll use it in the next step to rewrite the integral entirely in terms of u. This will allow us to perform a much simpler integration. Final integration. Okay, let's move on to slide 6. As you recall from the previous slides, we were integrating and had arrived at the integral. 2 times the integral of u to the power of 4 with respect to u, that's what we see here, represented as I equals 2 integral u to the power 4 do. Now, this is where a standard integration rule comes in handy. We're going to apply the basic power rule for integration, which states that the integral of u raised to the power n with respect to u is equal to u raised to the power n plus 1 divided by n plus 1, plus the constant of integration, c. So, applying that rule to our integral, we have 2 multiplied by u to the power of 4 plus 1 divided by 4 plus 1, plus c. This simplifies to 2 multiplied by u to the power of 5 divided by 5 plus c, and finally, we can write that as 2/5 u to the power of 5 plus c. So, I equals 2/5 u to the power 5 plus c. Excellent, we've now successfully integrated with respect to u. But remember, our original integral was in terms of x, so we're not quite finished yet. The next step, which we'll cover on the following slide, is to perform back substitution to express our final answer in terms of x. Back substitution. Okay, so we've successfully integrated with respect to our substituted variables, u and t, and now we have an expression in terms of those variables. But remember, the original problem was defined in terms of x, so we need to express our final answer back in terms of x. This process is called back substitution, and it's crucial to do it in the reverse order that we made the substitutions. Think of it like undoing the layers we applied. The last substitution we made was u equals tan t, so that's the first one we need to undo. So we replace u with tan t in our current integral. This gives us integral I equals 2/5 times tan to the power of 5 of t plus the constant of integration c. Now remember our very first substitution? We said that t equals the square root of x. So, to complete the back substitution, we replace t with the square root of x. This gives us integral I equals 2/5 times tan to the power of 5 of the square root of x plus the constant of integration c. And that's it. We've successfully integrated the original complex integral and expressed the answer entirely in terms of x. Let me state the final answer clearly. The integral of tan to the power of 4 of the square root of x times sec squared of the square root of x, all divided by the square root of x, with respect to dx, is equal to 2/5 times tan to the power of 5 of the square root of x, plus the constant of integration c. Now, before we move on, let's quickly review some common mistakes to avoid, which will be covered on the next slide, to ensure you don't fall into those traps when tackling similar problems. Common mistakes to avoid. Point number 1, neglecting the differential. It's incredibly common to make a substitution, for example, letting the square root of x equal t, but then forget to change dx to dt. Remember, when you're changing variables, you're also changing how you express the infinitesimal change in the variable. So, if you say the square root of x is equal to t, you must find how dt relates to dx. We did this in the example, finding that dt equals 1 over 2 times the square root of x times dx, and therefore dx equals 2 times the square root of x times dt. Always, and I mean always, calculate that derivative and the resulting differential immediately after making your substitution. It's a small step, but a crucial one. Moving on to point 2, incomplete back substitution. After you've integrated and have an expression in terms of your new variables, like u and t in our example, it's tempting to stop there. But remember, the original problem was defined in terms of x. If the question starts with x, your final answer must also be in terms of x, so you need to reverse the substitutions, step by step, until you've expressed your answer entirely in terms of the original variable. Don't leave your answer in terms of t or u, get it back to x. Finally, point 3, incorrect order of substitution. This is about strategy. In our example, we first simplified the argument of the trigonometric functions, the square root of x, before tackling the trigonometric functions themselves. Trying to substitute the trigonometric function directly, say, letting the tangent of the square root of x equal u, would likely lead to a much messier and more complicated integral. The general rule of thumb is to simplify the inner function first, the one that's nested inside another function, before moving outwards. Think of it like peeling layers of an onion. Okay, let's move on to slide 8, This slide highlights some common pitfalls students encounter when tackling integrals requiring multiple substitutions. Paying attention to these will save you a lot of frustration. So, keep these 3 points in mind as you practice, and you'll be well on your way to mastering multiple substitutions. Now, let's move on to the final slide, where we'll summarize the key takeaways from this entire section. Key takeaways. Okay, let's recap the key takeaways from working with multiple substitutions. This slide summarizes the main points to keep in mind as you tackle these types of integrals. First, we have the layered approach. Remember, we don't just jump into multiple substitutions for fun. We use them when a single substitution isn't enough to transform the integral into a solvable form. It's like peeling layers of an onion. Each substitution simplifies the integral a little more until we get to something manageable. Next is sequence. A good strategy is to first simplify the argument of your functions, what's inside the function. In our example, that was the square root of x then. After that first substitution, we focus on simplifying the function itself. Think of it as tackling the innermost part first, then working your way outwards. Now let's talk about the differential chain. This is crucial. Every time you make a substitution, say you let the square root of x equal t, you must also find how dx changes in terms of dt. We found that dx equals 2 times the square root of x multiplied by dt. And then, when we substitute it again, letting tan t equal u, we found do equals secant squared t dt. It's a chain reaction, and if you break the chain by forgetting to account for these differentials, your integration will be incorrect. Finally, we have the reverse process, or back substitution. Once you've integrated and have an expression in terms of your new variables, u and t in our case, you need to get back to the original variable x. And you do that in the reverse order of how you substituted. We first replaced u with tan t, and then we replaced t with the square root of x. If you try to do it in the wrong order, you'll end up with a mess. So, keep these 4 points in mind, and you'll be well equipped to handle integrals that require multiple substitutions. Remember to practice, and don't be afraid to revisit earlier examples if you get stuck.